Okay, this is lesson 6.1. Lesson 6.1 is matrices and systems of linear equations. So this first lesson kind of bridges the gap between chapter 5 and chapter 6. Chapter 5 dealt with systems of equations and solving systems of equations using elimination method and substitution method. 6.1, 6.3, and 6.4 introduce new ways to solve a system of equations. I'm not claiming that they're better or easier ways, they're just different ways in addition to substitution and elimination. And these new ways involve using matrices. So 6.1 is an introduction to what a matrix is and introduces a new method of solving a system of equations, which is this last topic here, Gaussian elimination. So we need to talk about the basics of a matrix. I need to introduce what an augmented matrix is. An augmented matrix is a direct relation to a systems of equations. We need to talk about elementary row operations. These are operations that can be done to a matrix to change a matrix. And then finally, the main topic of 6.1 is what's called Gaussian elimination. It's a way to solve a system of equations using only a matrix. So those are the topics. So, very general definition for a matrix. It's a bunch of numbers put into rows and columns, a rectangular array of numbers arranged into rows and columns. So here's an example of what a matrix might look like. The numbers are always grouped together using those brackets on the left and right side. As you can see, the 6, the -4, and the 3, that comprises a row, the top row. Second row would be 2, 8, and 7. So the rows are the horizontal components here. Columns are the vertical parts. So the 6 and 2 forms a column, -4 and 8 forms a column, and 3 and 7 forms a column. Now each individual number inside of a matrix is called an entry. So I'm going to circle the 3 here. That's just called an entry. Okay. Now in general, I've used specific numbers here. If we wanted to go more in general, the way that you describe the location of an entry in a particular matrix is by the row and then column. So I'm going to use the letter A. So this would be A1, 1 because it's the first row, first column. This entry here would be A1, 2. This would be A1, 3. The number 1 in front, or the number 1 that's first means it's the first row, first column, first row, second column, first row, third column. This one would be A2 now because it's the second row, first column. This would be A2, 2 because it's the second row, second column. This would be A2, 3. So on your homework, for example, if you're given a matrix and they say find the entry A2, 4, that would be the entry in the second row, fourth column. You just have to identify the number in that spot. Okay. Also important about a matrix is to be able to describe the size of the matrix. So the size of a matrix, other textbooks call it the order of a matrix or the dimensions of the matrix. Regardless, the size of a matrix is always described as the number of rows by the number of columns. Number of rows by number of columns. It always goes in that order. Rows first, and then columns. And it's important to be able to identify the size of a matrix. Maybe not for today's lesson of 6.1, but for 6.2, especially 6.2, when you have to add or subtract or multiply two matrices together, you need to be able to describe the size of the matrix. So this matrix here that we're looking at, this one that I'm circling, it has 2 rows and it has 3 columns. So for this particular matrix, it would be described as a 2 by 3. That's a 2 by 3 matrix. 2 rows, 3 columns. As far as basics of a matrix, that's about all you need to know. How to identify rows, columns, a particular entry inside of a matrix, and how to describe the size of a matrix. Now, the second topic we need to cover is what's called an augmented matrix. An augmented matrix is formed from a linear system of equations. So, for example, given a very simple system of equations here, 2x minus 3y equals 9, and 3x plus 7y equals 10. It's a linear system of equations with 2 variables. An augmented matrix is going to have the same number of rows equal to the number of equations. So this has 2 equations. So our augmented matrix is going to have 2 rows. Okay? Each column is going to be the coefficients of the variables. So we're going to have a column for the x coefficients, we're going to have a column for the y coefficients, and we're also going to have a column for the constants that are after the equal sign. So going across the top row, we're going to have 2, -3, and 9. Going across the bottom row, we're going to have 3, 7, and 10. And that would be the augmented matrix. So at this point, and at this point in your homework, all you would be asked to do is, given some kind of a system of equations, form the augmented matrix. Now we're going to be doing something with this a little later on, but for right now, that's all you would be expected to do. And vice versa, you may have to use an augmented matrix like this one to write a system of equations. So again, each row of an augmented matrix represents an equation. Since there are 3 rows, you're going to have 3 equations. Each column of the matrix represents coefficients of a variable. Now the last column are the constants after an equal sign. So since there are 3 columns before that, we're going to have an x, a y, and a z variable. So the system of equations that would match this augmented matrix, looking at the top row, would be 2x plus y plus 2z equals 7. Middle row would represent the equation 6x. Now there's a 0 here, meaning there's no y variable, so 6x plus 3z equals 4. And the bottom row represents the equation x plus y plus 2z equals 8. So as far as augmented matrices are concerned, that's, at this point, all that you really need to do with them is go back and forth between a system of equations or an augmented matrix. Now, third topic of the lesson is what are called elementary row operations. And essentially what they boil down to are all of the operations that you have done when you were solving a system of equations. For example, going back up here, if I wanted to solve this system of equations, I would most likely multiply the top equation by, let's say, -3, bottom equation by 2, and then I would add the two equations together in the hope of eliminating a variable. So I can multiply an entire equation by a number, and I can also add the equations together. And those are similar to, not just similar, those are exact same operations that can be performed on a matrix. So here are the three row operations. You can multiply a row by a non-zero constant, so it needs to be non-zero. If you multiplied a row by zeros, you'd end up with just zeros in that row. And that would be like multiplying an equation like I did just barely. I multiplied one of the equations by -3. That was multiplying an equation or multiplying a row by a non-zero constant. Second row operation is to add a multiple of one row to another row. That's exactly what we do in the elimination method. You multiply one, possibly two equations, and then you add the two equations together. So as you recall, in the world of matrices, a row represents an equation. So you can add a multiple of one row to another row. Now the third one, interchanging rows. Going back up here, if I were to take this top equation and change it so it was at the bottom, you would still have the same system of equations. So I'm just taking the top equation, moving it underneath, so now it's the bottom equation. It doesn't really do anything to affect the solution to the system of equations. So that would be like interchanging rows. If I wanted to take this middle row here and move it down to the bottom, and move the bottom row up to the middle, if we were to solve that matrix with Gaussian elimination, just interchanging rows would not affect the solution. So sometimes interchanging rows can be helpful in solving an equation, or solving a system of equations. Let's practice some row operations. I've got a matrix here. So I want you to copy the matrix. And this is the notation here, what I've got written to the right side. This is the notation for performing row operations. So, reading this string of commands here, 2 times R2. R2 means row 2. So this first part of the command says we're going to take row 2, all of the entries in row 2, and multiply them by 2. After that, we're going to add all of those new entries to the entries in row 3, just beneath them. Now, performing a row operation always creates a new row that replaces one of the original rows in the matrix. So that's what this means right here. All of these operations are going to replace row 3. So row 3 is going to change and become a new row. We're going to end up with a matrix of the same size. So it's still going to be 3 rows, 4 columns. So following along this string of commands, you're going to want to do this to one entry of row 2 at a time. So starting here with the 1, now you follow what the row operation is, 2 times row 2. So all of the entries here in row 2 essentially going to be multiplied by 2. And then each of these numbers are going to be added to the numbers in row 3. That's what this operation says. So 2 times 1, that makes a 2. But then 2 plus the 3 beneath it makes a 5. And since all of these entries are replacing the entries in row 3, I'm going to put a 5 for the new entry in row 3. And I move to the next part of row 2. 2 times this 2 makes a 4. 4 plus -1 is 3, so the new entry in row 3 is a 3. 2 times this negative 2 is negative 4. Negative 4 plus 5 is 1, so this entry becomes a 1. And finally, 2 times 10 is 20. 20 plus 14 is 34. Now, according to this row operation, the only row that was affected is row 3. Row 3 is now changed. The other rows stay the same. 1, 2, negative 2, and 10. For the middle row, top row is 1, negative 1, 3, and 4. So the part of the homework dealing with this is just going to ask you to practice row operations. You'll be given a certain string of commands, and you have to perform those row operations to make up a new matrix. So one to practice here. I want you to write it down, and I want you to write this row operation down, and then go ahead and hit the pause button so you can have time to work on it. So, this is what should have happened. Now we're multiplying row 1 by negative 4. So this entire row is going to be multiplied by negative 4, and then those entries are going to be added to row 2, but ultimately that's going to affect row 2. So row 2 down here should be a new row of numbers. Okay, so negative 4 times 1 is negative 4, and then negative 4 plus 4 is 0. Moving on to over here, negative 4 times 3. It's negative 12 plus 6 is negative 6. And then negative 4 times 8 is negative 32. Negative 32 plus another negative 2 is negative 34. So that was just practicing a basic row operation. Now, I'm going to use this to kind of move ahead a little bit in the lesson and give you a preview of why these row operations can be so useful. Recall where this, or what this augmented matrix represents. This augmented matrix represents a system of equations. The top row is an equation of x plus 3y equals 8. The bottom row is an equation of 4x plus 6y equals negative 2. Now what we've done with this row operation is create a new matrix, but this new matrix still represents the original system of equations. And in particular, if you pay attention here to the bottom row, there's a 0 where the x coefficient is. So this new row represents the equation negative 6y equals negative 34. It's very easy now to solve for y. By dividing by negative 6, we get 34 over 6, or 17/3. So we now know the value of y. And if we go back up here to this row represents the equation x plus 3y equals 8. And if we take this value of y and substitute it in there, we get x plus 3 times 17/3 equals 8. The 3's cancel. And if you subtract 17 from 8, that'll give you the value for x. X equals 9. So using only one row operation, we were able to figure out the value of y and then backward substitute. And this is precisely what Gaussian elimination is. It's performing row operations until you get to a point in a matrix where you can solve for one variable and then work your way back up the matrix to solve for the remaining. Now, the particular form that we want the matrix to be in is what's called row echelon form. So I've got two matrices here. One is a 2 by 3, this one's a 3 by 4. I'm going to posit, well, I'll just give you some time here to write these two. Just write the two matrices down. Don't worry about this over here yet. But both of these two matrices are in what's called row echelon form. And this is what you want your matrices to look like when you're doing Gaussian elimination. And this is actually the matrix from the last example. If you look at the bottom row, you can clearly see that y equals 17/3. If you're in the case of 3 equations and 3 variables, if you look at this bottom row, you can clearly see that this right here represents an equation that z equals 4. Then you can work your way back up to this middle equation to get y, and then work your way back up to the top equation to get x. Now, key characteristic for row echelon form, if you haven't noticed yet, is if you look at each row, the first non-zero entry in each row is a 1. There's a 1 right here. That's the first non-zero entry. Here there's an entry of 0, so it doesn't really count. The first non-zero entry here is 1. And in the bottom row, the first non-zero entry is a 1. Same thing here. If you look at both the rows, the first entry is a 1, and here the first entry that's not a 0 is a 1. That's a key characteristic of a matrix in row echelon form. So this is what's called the main diagonal, starting at the top left and going to the right. So in this main diagonal, you have only 1s. That's the most important characteristic of row echelon form. That's what I've started to write over here. These are the conditions to be row echelon form, the leading entries. So these are all 1, and those leading entries are in the main diagonal. And it does occur from time to time that you have a row of all 0s, or all 0s except for the last number. If that's the case, that row needs to be at the bottom. So you may have homework questions where you're given a matrix and asked if it is in row echelon form. It's a simple yes or no answer, so you've got to consider, are there 1s in the main diagonal? And also you have to have 0s beneath it. That's another characteristic. So right here, you have 0s underneath the 1s in the main diagonal. Here you have a 0 underneath the 1s in the main diagonal. So if that's the case, then the answer is yes, it's in row echelon form. If not, then the answer would be no, the matrix is not in row echelon form. So this brings us to the last topic, what's called Gaussian elimination. Gaussian elimination is a process that reduces an augmented matrix to row echelon form. And why is that so important? Well, this matrix up here still represents a system of equations because it's an augmented matrix. And when it's in row echelon form, if you start at the bottom, like I was saying earlier, this represents the equation z equals 4. And if you come up here, this represents the equation y plus 3z equals 6, but now that you know that z equals 4, 3 times 4 is 12. If you take 12 from 6, you get y equals -6. And then you can go up to the top row and find the value for y, or for x rather. Now, something you have to understand about Gaussian elimination, it's not a shortcut, and honestly, quite often it is longer than solving the system using the traditional elimination method that you learned back in chapter 5. Why learn it if it's longer? Well, it's how a computer system solves a system of equations. A computer system can solve it almost instantly just by using numbers in a matrix rather than variables. So if you ever are planning to become a computer engineer or something like that, you have to know how to program computer programs. So this is how a computer thinks, so only with ones and zeros and numbers. And anyway, first step would be to transfer the system of equations into an augmented matrix. So going down the first column, you have got a 1, a 1, and a 3. Middle column would be a negative 1, 2, negative 1. Third column is 3, negative 2, 5. Last column is 4, 10, and 14. And you can see what we've been given is not in row echelon form. If we look at this main diagonal here, those aren't ones, which they should be. And if you look here, those should all be zeros. So there's a little bit of work to do before we can get this into row echelon form. And it needs to be done in a particular order. First goal should be to get this to be a 1, which it already is. And then beneath that, you want to get this entry to be a 0, and then get this entry to be a 0. Okay? Once that's accomplished, you take a look at this. You want that to become a 1, and then beneath that, you want to make that a 0. And then you get that to be a 1. So again, you start at the top left. If it's not a 1, you make it into a 1, and I'll show you how to do that with another example. But once it's a 1, you make zeros beneath it. Then you move over here to this entry and make this a 1, and make zeros beneath it, and then finally you make this into a 1. So let's see what this looks like. Now the row operations before were already given to you. I told you the row operations to perform. When you're doing Gaussian elimination, you've got to come up with the row operations on your own. And they're not just random row operations, they need to be designed row operations for a particular purpose. Right now, since we already have a 1 as the leading entry in the top row, our purpose is to get that to be a 0. So we need to combine certain rows in this matrix together in order to make a 0 right here in this first entry of the second row. So what we're going to do, I'm going to multiply row 1 by negative 1. And again, these are not just random row operations. I'm going to multiply row 1 by negative 1, and then I'm going to add that to row 2. What's the purpose of that? Well, if I multiply the top row by negative 1, and then add that to row 2, and make that equal row 2, what that's going to do is put a 0 right there, exactly where I want it. Okay. So this row operation is going to replace row 2. So imagine row 1 is being multiplied by negative 1. Negative 1 times 1 is negative 1. Negative 1 plus 1 is 0. Now over here to the second column of row 1, negative 1 times negative 1 is 1. 1 plus 2 is 3. Negative 1 times this 3 is negative 3. Negative 3 plus negative 2 is negative 5. And then negative 1 times 4 is negative 4. Negative 4 plus 10 is 6. And only row 2 was affected, so okay. So we've taken care of that. That needs to be a 0. Now this 3 right here needs to be a 0. We're going to perform another row operation. That's why it's very helpful to have a 1 above where you want to have all the zeros. If I'm trying to get rid of a number, 3 for example, then you can just multiply the 1 by -3 and add them together. So that's so important to have 1s along your main diagonal, because then it makes getting zeros beneath it a lot easier. So now I'm going to do -3 times row 1, but now I'm going to add that to row 3, and that's going to replace row 3. So row 1 is now going to be multiplied by -3. So -3 times 1 is -3. -3 plus 3 is 0. -3 times -1 is 3. 3 plus -1 is 2. -3 times 3 is 9, or -9 rather. -9 plus 5 is -4. And then -3 times 4 is -12. -12 plus 14 is 2. Okay. So we'll make progress. We've got a 1, a 0, and a 0, exactly where we want them. Okay. Our next task should be to get a 1 here and a 0 beneath that. Now I mentioned earlier, if you don't have a 1 where you want to have a 1, the best thing to do is just to multiply that row by the reciprocal of the number. Here's what I mean. I'm trying to get this 3. I'm trying to turn this 3 into a 1. So if I take 3 and multiply it by 1/3, what do I get out of that? I get a 1. So I'm not trying to get this to be a 0, so I'm not going to try to combine that with any other row. I'm just going to stick with row 2. And one thing I could do is multiply row 2 by 1/3. Now there is a little bit of, it's not really a problem, but something to consider. 1/3 multiplies 3 really easy. 1/3 multiplies 6 really easy. 1/3 doesn't multiply -5. You end up with a fraction. What I'm actually going to suggest is that you swap row 2 and row 3. We're going to interchange row 2 and row 3. So the row at the bottom is not going to be the row at the bottom, 0, 2, -4, and 2. I'm going to write that in the middle. And then the row that was in the middle, I'm going to put that at the bottom. Didn't do anything to the top row. Now why do that? Well, now look at the middle row. I want to get this to be a 1 still. And if I'm trying to change the value of a number into 1, you can just multiply it by its reciprocal. So if I want to change 2 into 1, I can just multiply it by 1/2. And that's going to turn 2 into a 1. And then at the same time, you'd have to multiply everything else by 1/2. And -4 and 2 are both easily multiplied by 1/2. So now I'm going to perform that row operation. 1/2 times row 2, and this is going to equal row 2. The reason I swap rows is every entry in row 2 can be multiplied easily by 1/2 and still end up with a whole number. So row 2 becomes 0, 1, -2, and 1. All the other rows stay the same. Okay, remember the steps. 1, 0, 0 on that first column. Then if we move over, this should be a 1, which it now is. That should be a 0. So the next task is to get this to be a 0. like we were doing earlier on in this problem, if you want to get a 0, you multiply the 1, the leading entry above it, by the opposite of that number and add them together. So I'm going to take and multiply row 2 by negative 3. So you multiply row 2 by negative 3. What that's going to do is put a negative 3 right here in this entry. And then if I add that negative 3 to this 3, that's going to make this turn to 0. So now you add this to row 3, and it's going to replace row 3. And one thing that's also important is when you perform a row operation, you don't want to undo any of the other changes that you've made. You don't want these to become anything other than 0. So just pay attention to the row operations you're doing. Negative 3 times 0 is 0. 0 plus 0 is still 0. And then over here, negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times negative 2 is 6. 6 plus negative 5 is 1. Negative 3 times this 1 here is negative 3. Negative 3 plus 6 is 3. Okay, now if we check our progress, we've got 1s in that main diagonal, and we've got 0s beneath them, so we're actually done. We've got this row into row echelon, or we've got this matrix into row echelon form. So the next task is to figure out the value of x, y, and z. So going to this bottom row, if you remember this column right here that I'm highlighting, this column represents coefficients of the z variable. So the coefficient of 1 just means z. Z is equal to 3. This row represents the equation y minus 2z equals 1, and this row represents the equation x minus y plus 3z equals 4. Now you can work your way up and backwards substitute. Z equals 3. And you substitute that in there for that z. So you get y minus 6 equals 1, which means that y equals 7. Now you take that value and plug it in there, and we already knew that z was equal to 3, so you plug that in there, and you get an equation of x minus 7 plus 3 times 3, which is 9, equals 4. Negative 7 plus 9 is 2. So you have x plus 2 equals 4, and finally x equals 2. So z equals 3, y equals 7, x equals 2. And as before in chapter 5, I would ask that you write your solution as an ordered triple so I can find it easier on your page. I know exactly what you're thinking. This is by far the longest, most terrible way to solve a system of equations. By hand, probably right. But the fact of the matter is you still have to learn how to do it. It does get quicker and easier with practice. So I'm going to do you one here to practice on your own. After you write it down, I would ask that you pause the video, allow you time to work on it, and then I'll go through and show the solution. So let's do 4x plus 8y minus 4z equals 4. 3x plus 8y plus 5z equals negative 11. And negative 2x plus y plus 12z equals negative 17. I'm going to help you get started here and then I'll have you pause the video. First step would be creating the augmented matrix. So 4, 3, -2, 8, 8, 1, -4, 5, 12, 4, -11, -17. So there's your augmented matrix. Remember the order for Gaussian elimination or the process. You want to get this to be a 1, and then zeros beneath it. Then this should be a 1, a 0 beneath that, and then that should be a 1. So the first problem is this 4 right here. It's not a 1. Anytime you're trying to create a 1 out of a number, the easiest thing to do will be to multiply it by the reciprocal of that number. So the reciprocal of 4 is 1/4. So I need to take 1/4 times row 1. That's going to replace all the entries just in row 1. So the new entries in row 1 become 1, 2, -1, and 1. So I would ask now that you pause it for a moment and at least get as far as you can. Try something. You know, the next step would be to get zeros here, and then get a 1 here and a 0 there. All right. I'm trying to get a 0 right here. Anytime you're trying to create a 0 out of a number, you need to add it to the opposite of that number. 3 plus -3 would make that turn into 0. So what that's going to require is that you multiply this by a -3. The top row needs to be multiplied by -3. -3 times row 1. Add that to row 2, and that's going to replace row 2. Okay. So I'm not going to write it down because it's going to get a little messy here in a second, but you just need to remember that this entire top row is being multiplied by -3. So -3 times 1 is -3, and then -3 plus 3 is 0. Now move over here. This is also multiplied by -3, making -6. -6 plus 8 is 2. This is multiplied by -3, making 3. 3 plus 5 is 8. And then this is multiplied by -3, adding to -11, makes -14. Now to save time and space on your paper, you can use one arrow here to describe 2 different row operations. As long as the 2 row operations are affecting different rows, I'm going to perform this row operation here. 2 times row 1 plus row 3 equals row 3. Now what this is going to do is change row 3 because this whole operation equals row 3. But now I'm multiplying the top row by 2. In particular, that's going to place a 2 right here, and when I add that 2 to this -2 in row 3, that's going to create a 0 in row 3. So now the top row is being multiplied by 2. 2 times 1 is 2. 2 plus -2 is 0. 2 times this 2 is 4. 4 plus 1 is 5. 2 times -1 is -2. -2 plus 12 is 10. And then 2 times 1 is 2. 2 plus -17 is -15. And none of these row operations affected row 1, so row 1 stays the same. So we've got 1, 0, 0. The next task should be to get this to be a 1. If you're trying to change a number into 1, you multiply it by its reciprocal, so row 2 needs to be multiplied by 1/2. 1/2 times row 2 equals row 2. The reason I didn't swap any rows here is every single entry in row 2 can easily be multiplied by 1/2, and you still end up with a whole number. So 1/2 times 0 is still 0. It's important that that stays at 0. 1/2 times 2 is 1. 1/2 times 8 is 4. And 1/2 times negative 14 is negative 7. That's the only row operation I'm going to do with that arrow. Okay, so now that that's a 1, it should be a 0 beneath it. If you're trying to create a 0 out of a number, remember is you look to the 1 above it, multiply it by the opposite, and then add together. So I'm going to multiply this by negative 5. Negative 5 times row 2, add that to row 3, and that becomes row 3. Negative 5 times 0 is 0. 0 plus 0 is still 0. It's important that you keep the 0 there. Negative 5 times this 1 right here is negative 5. Negative 5 plus 5 is 0. Negative 5 times 4 is negative 20. Negative 20 plus 10 is negative 10. And then negative 5 times negative 7 is 35. 35 minus 15 is 20. Yeah. I'm just going to give you a little hint here. Technically, is this matrix row echelon form? Well, no, it's not. If you look at the main diagonal there, they're not all 1s. But there are 0s underneath them. As far as what I care, this is different than the homework. If the homework says go row echelon form, you need to go into row echelon form. If this were a test question, and all I'm asking you to do is solve the system of equations using Gaussian elimination, you can actually stop with row operations here. This bottom row represents the equation negative 10z equals 20, and you can solve it from there. If you divide both sides by negative 10, you get z equals negative 2. And I move up and you have y plus 4z equals negative 7. If you plug the negative 2 into that z, you get y minus 8 equals negative 7. So y equals 1. Move up to the top row, x plus 2y minus z equals 1. If you plug in the known values for y and z, you get the equation x plus 2 times 1 minus negative 2 equals 1. Minus a negative becomes plus, so this is 2 plus 2 is 4. X plus 4 equals 1, so x equals negative 3. The solution becomes negative 3, comma 1, comma negative 2. Like I've said before, last thing on everybody's mind during a test is to check answers. However, with so many steps and so many processes and adding and subtracting and multiplying, it's very easy to make a small mistake somewhere, especially if it's early on. It's going to mess up the whole rest of the answer. So it would never ever be a bad idea to go back and check your answers and make sure the answer works in all 3 equations. And it really doesn't have to take that much time. Remember, the solution was negative 3, comma 1, comma negative 2. So 4 times negative 3, that makes negative 12, plus 8, plus another 8. 8 plus 8 is 16. 16 minus 12 equals 4, so it checks there. Middle equation, 3 times negative 3 is negative 9, plus 8, minus 10. Negative 9 plus 8 is negative 1. Negative 1 minus 10 is negative 11, so it checks there. And finally, negative 2 times negative 3 is 6. 6 plus 1 minus 24. 7 minus 24 is negative 17. Last thing here involving Gaussian elimination and using this process to solve a system of equations. You may recall from section 5.2, even 5.1, not every system of equation has a unique solution. Sometimes there are infinitely many solutions. Sometimes there are no solutions. So we're going to kind of jump into a problem almost all the way complete. So we've gone and we've made an augmented matrix and we've gone through Gaussian elimination. But let's say when we finish Gaussian elimination we end up with this matrix right here. 1, 0, 0, 0, 1, 0, -7, -3, 0, -5, 1, 0. So we've already gone through all the whole process of the last example, and we're here, and now we're scratching our head wondering, all right, what does this mean? It's still technically row echelon form. Remember, one of the stipulations is that if there's a row of all zeros, it's at the bottom, which this one is, and we have ones along the main diagonal. So the bottom row represents the equation 0 equals 0. Now hopefully that looks familiar. Whenever you see this in the process of solving a system of equations, remember that means infinitely many solutions. So there are infinitely many solutions. Okay. Back in 1010, that's where you would have stopped. But back in section 5.2, the next step would be to represent the solutions using a parameter t. So you still would need to do that in this case. The way that it works with 3 equations and 3 variables is you let z equal t. And then you have to find out what y and x equal in terms of this new parameter t. We don't get much from the bottom row except for the fact that there are infinitely many solutions. The middle row, however, represents the equation y minus 3z equals 1. If we now make the substitution that z is equal to t, we end up with y minus 3t equals 1. Quite often students forget what happens next. We're not solving for t. We already know what t equals. T is equal to z. Now we're solving for y. So if you add the 3t over, you get y equals 3t plus 1. So now we know 2 of the variables. We know that z is equal to t, and we know that y is equal to 3t plus 1. We're just missing x. We get that from the top equation. The top equation, or the top row, represents the equation x minus 7z equals -5. And we make the substitution for z. We make a substitution there. X minus 7t equals -5. Add the 7t over and you get x equals 7t minus 5. And now we know all 3 variables, so you're ready to represent your solution as 7t minus 5, comma, 3t plus 1, comma, t. The other situation to watch out for in Gaussian elimination is no solution. And again, we're just going to skip into a problem kind of part way through. Let's say we've done Gaussian elimination to end up with, and you know, it doesn't matter what those top 2 rows. Let's say the bottom row is 0, 0, 0, 6. And obviously you'd have numbers in row 1 and row 2. Okay, but if you're to this point and you look at the bottom row, this represents the equation 0 equals 6. 0 does not equal 6. There aren't any variables to solve for either. It's not infinitely many solutions because 0 doesn't equal 0. This, you may remember, is when you would say there are no solution. There's no solution to this system of equations represented by this augmented matrix. So there it is in a nutshell. I know you're not allowed to use graphing calculators, but just so you can see how quickly this can be done on a graphing calculator or any computer system. This isn't something you'd be able to do during Math 1050, but if you're ever in a situation in another class that allows graphing calculators, it may be helpful to see it. So matrix A is a 3 by 4. I need to type in the entries here. So I've typed in the entries into matrix A. Now go back into the matrix menu, math, and go to REF, that stands for row echelon form. I want the row echelon, try that again, row echelon form for matrix A. We get z equals -2, and then from the rest you could get the rest of the values like we did in that example. So for a computer or for a calculator, it goes very quick. Not a very painless process. All you got to do is basically punch the numbers in. You, fortunately, have the wonderful opportunity to learn and to perform it by hand. So that's lesson for Chapter 6, Section 1.